TEG Engineering. I wanted to give credit to Bill Hazelton and Dwayne Rogers from St. Clair County who helped me put together this presentation. And if during the course of this presentation, if you have questions, go ahead. I can see in the chat, I can see questions. So I like to kind of answer questions as I go. So if you have some questions, please please write them down as we go here. All right. See if I can get this to advance. I want to give you a little history about TEG Engineering. We were started in 2007, group of structural engineers. We're pre-qualified in both Texas and Michigan with the DOTs. We mainly service precasters and contractors. We specialize in what we call precast concrete heavy civil construction. We are members of AASHTO, ACI, PCI, National Steel Bridge, and Short Span Steel Bridge Alliance. Background on the actual project and location of the project. This project is located in St. Clair County, Michigan, which is just north of Detroit. St. Clair County is a county with that services 226 bridges, and of those, they have, if you look in the lower right on the slide, they have 20 in serious condition, critical condition, and 21 in poor condition. The problem that they are encountering is Michigan Department of Transportation actually does have a local agency program where counties can submit and get funding to replace bridges. The problem currently is they're just in that local agency MDOT program. There's just not enough funding to service the 80+ counties that are out there. So St. Clair County has chosen to kind of take it on their own and use their own funding to replace and upgrade their critical bridges. I want to talk about two specific bridges that we replaced the superstructures for, which are both on Marine City Highway. One structure 408, which was a 25-foot span bridge on a 90-degree skew, and the other 409 was a 36-foot span on a 45-degree skew. These bridges are about half a mile apart, and they were done in parallel. So the county crews worked on one bridge, closed the road, and then opened it up to that bridge, and then went down 2 weeks later and worked on the second bridge. We'll talk a little bit about that later. The bridges are, again, as I said, they're on Marine City Highway, which is a rural road, but it's a very heavily trafficked rural road. It's got more than 16,000 ADD. And it was very important to the county to maintain that that traffic as much as possible. And really, if they had to close the road for as little time as possible on detour routes. The goals of the superstructure replacements were, really, the main goal was to add an additional 60 years of service life to these bridges. The county, in looking for advantages and ways to optimize their construction and their costs, were they wanted to use as many of the existing abutments or existing features as possible, and the existing abutments were in good condition. So we maintained the existing abutments. We also maintained the superstructure depth. That was important so that we could do as little approach work as possible. The roadway in this area was in good condition. We just needed to replace the bridge superstructure. We wanted to maintain constructability by the county crews, and then it all had to be designed for MDOT HL 93 modified loading. And MDOT requires their modified loading is a 20% increase in the AASHTO HL 93 live load. Again, a big big aspect of this job was to get an additional 60 years service life on these bridges. In Michigan, we do use a lot of de-icing salts, and we have a lot of concrete deterioration. And the county engineer felt that pre-stressed concrete box beams does not give him the 60 years of service life that he was looking for. So what they looked at were really three options. And again, why do counties, why do local agencies choose the options they choose? It's all about cost. We want to find an option that will meet the goals that we have set forth, and do it for as cost effectively as possible. So in that regard, the county went and looked at three options. One was a steel bridge with corrugated steel decking and an HMA overlay, and that came in at $75,000. Next was full reconstruct with precast concrete box culverts, and that bid came in at $63,000. And the chosen system was a pre-stressed, a press brake form tub girder, galvanized, with a precast deck, and the cost for that came in at $57,000 for the structure itself, and then all of these have additional items that need to be done once they are installed. In the end, the county engineer estimated that the galvanized prefabricated press brake formed tub girder option was 10% cheaper in this application. The system chosen was called the Con-Struct prefabricated bridge system. So what I want to talk about now is a little bit of history of the system that was actually chosen. Con-Struct was developed by TEG in coordination with FHWA in 2003. It was really developed for ABC construction, accelerated bridge construction, and the intent was to, back in 2003, FHWA had the Get In, Get Out, Stay Out initiative, and really the intent was to replace superstructures and install bridges much faster than conventional construction. What we found over the years is that the Con-Struct system is actually a good system, not just for accelerated bridge, but just for any kind of conventional construction, and the replacement to pre-stressed concrete box beams maybe give a little longer service life, especially when we use galvanized press brake tub girders. This system has been approved for use in 5 states and in Canada with Ministries of Highways in Saskatchewan. So getting in again to the Con-Struct bridge specific components. What we have here is we have some pictures of a project we did in Boone County, Missouri. It was an FHWA funded project. It was a GRS IBS system, GRS geosynthetic reinforced soil, which are the abutments, the block walls you see there are geosynthetically reinforced soil. And the IBS, the innovative bridge system, was the Con-Struct bridge system. If you see in the picture to the right, we actually cast wide back walls that also served as the footings that were set with the superstructure. So the footings were set directly on the reinforced backfill on this specific job to limit the amount of cast-in-place concrete that needed to be done. Again, advantages of kind of the ABC accelerated construction. Press brake form tub girders really have been around since the 1970s. They were researched back then. The big question we often get is, well, why now? Why, if these have been around for a while and they haven't been used for a while, why now are they a choice, a good alternative for bridge superstructures? One is the industry has really upgraded to be able to do things, to provide the elements in a fashion we need them. One is we have hot dip galvanized up to 80-foot long lengths of the press brake form tub girder. Those are done. Typical biggest tank galvanizing tank is 60 feet, but you can progressively dip the tub girders and get a hot dip galvanized coating up to 80 feet long. Also, press brakes in the United States have increased in length, where now we have many options for 60-foot long press brakes that can form girders in up to 58 feet continuous lengths. The longest we did was continuous was 59 feet 6 inches, as long as that press brake would allow. Additionally, back in when this was originally being developed, it was more looking specifically at the tub girder itself. Now we're looking at the whole system, not just a press brake tub girder, but a press brake tub girder bridge system. And to do that, we got the precast concrete industry involved and looking at a manufacturing process to provide a completely fabricated bridge system to the construction site. Additionally, FHWA has been extremely involved lately over the last really 20 years, and really have stepped it up with the programs lately for trying to deploy new innovative materials and funding for accelerated bridge construction, ultra-high performance concrete, and as we talked about, the GRS abutment systems. So the Con-Struct system was developed in Michigan and was researched by Michigan State University through MDOT. MDOT actually did their own project in 2011. Michigan State University provided research to show that the tub girder bridge system provided more capacity than as designed per AASHTO LRFD. Additionally, MSU looked at deck joint options, and we looked at, well, what would be the service life of a bridge that were built in this fashion. And again, the goal was to have a 75-year service life. And additionally, we found that we can fabricate and provide installed cost for these bridges at basically that of a conventionally constructed concrete precast pre-stressed concrete bridge. Another development was the Short Span Steel Bridge Alliance became involved in research with this system, looking at modular press brake form steel tub girders, and have been doing research through West Virginia University, Marshall, and the University of Wyoming. They have been also looking at the overall capacity of the system and assessing details such as deck to girder studs details, and also looking at distribution factors and fatigue. We'll talk a little bit more about fatigue loading later, but really really their research is looking at the applicability of this system with AASHTO LRFD design. Getting specifically into the press brake form steel tub girder, you can see here the press brake on the left. That is the die, and that is usually the limiting factor. Usually press brake is 60 foot long. The die itself comes in lengths up to close to 60 feet long. So we found that 59.5 was about as long as the die we could find. The big advantage with the press brake form tub girder is that there are no welds, no web to flange welds, and the bend radius is per AASHTO and AISC requirements at 5 times the thickness of the plate, which means there's no brittle fracture when you are when you are breaking these elements, and therefore you basically up to 60 feet long, you have one plate that that is continuous without any welds, without any critical fatigue elements. However, we still design, we found an AISC cold formed angle research back in the 1980s that attributed fatigue resistance to about an AASHTO category B in cold formed angles. So we still use an AASHTO category B fatigue requirement in our designs. Moving on, the next elements of the press brake form steel tub girder are the shear studs, which are a typical detail approved throughout the United States, and all designed per AASHTO LRFD requirements for size and spacing. So we weld shear studs to the top flange of the tub girder. Once we weld the studs on, the whole unit is then hot dip galvanized. If you see on the right, that is our 80-foot long press brake tub girder being progressively dipped to get a coating along the whole length, a continuous coating along the whole length. We did have to weld splice that to get it 80 feet long. We spliced a 50-foot and a 30-foot piece together. The galvanized coating provides a 60-year plus coating life, and that's just the coating life. We actually have one here locally in Ottawa County, Michigan. Again, Michigan likes to use their de-icing salts, and the bridge was built in 1966. Span lengths up to 50 feet long, and currently inspection reports show no current signs of any coating deterioration on those galvanized I-beam girders. So we really believe that the hot dip galvanizing really is a very effective protection for the steel tub girder. The next element is the precast concrete deck. The method for manufacturing the precast concrete deck is to precast deck panels, full depth deck panels that are individually placed on the tub girder, and then grouted in. This is a typical construction sequence or manufacturing sequence for full depth concrete panels. What we do is we have shear pockets that then accept the shear studs, and once the deck panels are then placed on the tub girder, we fill those pockets and the joints between the individual precast panels with a non-shrink high strength grout. For this particular project, we used an MDOT type H1 because it was an MDOT project, and most states have pre-qualified grout, high strength grout systems. I did want to note on the right that's the top of the precast panel. However, that is now we standardly transversely tine the panels if they're not receiving a full overlay, precast overlay. This particular panel on the right, that is not a tining. That's an awful rough tining. That is a roughened surface because that is going to receive a 1.5 inch precast overlay on top of the deck panels, and we'll talk about a little bit about that next. In Texas, our standard is to provide a 1.5 inch precast overlay on top of the deck panels. We do that with the standard TxDOT Class CO overlay mix. We also add about 30 pounds per cubic yards of steel fiber, additional silica fume for toughness, and our mix design is a self-consolidating concrete, which flows very easily, flows into all the pockets. We use that to flow into the deck joints between the precast panels, and then finish it as typical with a transverse tining. finally, about the system, really what we wanted to, going back, one of the objectives of at least of the Con-Struct system was to make this precast deck with a press brake form tub girder standard to AASHTO, and we design it all per AASHTO LRFD. It can be load rated per AASHTO AASHTOware load rating software, and it's compatible with many load rating software and spreadsheets that are out there. Again, it follows AASHTO LRFD, and we provide easy to follow math CAD calculations that can be easily checked and verified. Lastly, environmentally, the press brake form tub girder system here, it uses about 50% of the material that a conventional pre-stressed concrete I-beam would use. The difference too is we use much more steel than a pre-stressed concrete I-beam, which steel is the most recycled product in the world, and is about 88% of steel is recycled. We have basically half the volume of a comparable, same span length, same deck thickness pre-stressed concrete I-beam. All right, wanted to get into the actual case study now. For the specific case study, again, the pictures you see here are the first element. It's a 25-foot span for the bridge 408 structure. We start fabrication 2 to 3 months typically before construction starts. Obviously, we've got to produce an entire bridge prior to it being needed on at the actual construction site. So for this project, the bridge units were fabricated at ADL in Portland, Michigan, which is relatively Lansing, Michigan, which is about 100 and so miles away from the St. Clair County construction site. The deck panels are fabricated in with quality control overseen by the county and their consultant. So all this was inspected and looked at by an independent consultant at the plant, at the precast plant at ADL. So we started demolition, as you see here, on October 9th of Bridge 408, which is the 25-foot span, 90-degree bridge. 409 was started about a month later after 408 was installed. County crews came out and in 2 days removed the existing superstructure. Once the superstructure was removed, they placed riprap for scour protection in front of the abutments and patched any problem areas on the existing abutments. We used a T17 polymer concrete by Transpo Systems, or Transpo Industries, and you'll see later we use that also for deck joints. So first thing was repairing the abutments and placing riprap. Once that was done, on Thursday we came in and delivered the 6 pre-stressed precast concrete galvanized tub girder bridge systems. You can see here on the right or on the left, they are placing the bearing pads. These are set on conventional elastomeric bearing pads, and you can see on the left they are placing the bearing pads. And these particular units had an integral back wall, so we also precast a back wall on these bridges, so the county would not have to do any cast in place work in the field, and you'll see that on some next slides. So once the abutments were ready, the county came in and used their own, on the 25-foot span, the units were only about 18,000 pounds each unit. So the county was able to use their excavator to install the 6 bridge units. On the 35-foot span, 409 bridge, those units on those were, they were 45-degree skew and 35-foot span, and the units were about 26,000 pounds, which exceeded the capacity for the reach required of the county's excavator. So they actually rented a crane. You can see on the right there, they had to rent a crane to set those units. 6 units on both bridges were brought in 8, 9 o'clock in the morning, and all 6 units were placed before noon, so about 4 hours to set 6 units. We typically estimate, once they get going, about a half hour per unit for setting these bridge units. Again, you can see there the integral back walls that helped the county, because then they didn't have to come back and do any cast in place back wall work. Next, we talked about the Transpo T17 polymer concrete being used for patching. For this project, we talked about using ultra high performance concrete for the deck joints. We have deck joints that were already designed for UHPC. The county and MDOT liked the performance of the polymer concrete, the T17. So TEG went to Transpo Systems, or Transpo Incorporated, and had them test the T17 mix for development length and pullout of a number 5 bar cast into their concrete. So basically what we did is, through testing provided by Transpo of the T17 polymer, we designed and modified our UHPC joint to fit their polymer concrete. Their polymer concrete achieves a strength of about 9,000 psi, but the nice thing about it also is sometimes UHPC takes a little longer to set up, where the polymer concrete, within 4 hours, you're achieving strengths over 6,000 psi. So very fast setting, sets up, and nice, because the next day you can basically bring out traffic and start continuing with your construction work. Once the joints were cast, the next thing to do is obviously put down guardrail posts, and you can see there on the left they're applying asphalt to the approaches. Again, we wanted to minimize the amount of asphalt amount of road work that needed to be done. We only needed to go out 20 feet. We matched the existing structure depth. If you see back, I'm going to back up. If you see these superstructure units, they are relatively deep compared to the span. The reason the press brake form tub girders were designed to be that deep is because we wanted to match the existing steel beam depths that were out there, so that we could limit the amount of approach work the county had to do. And so we matched the depth, and you can see here that the bridge came in matching depth, and they only needed to do 20 foot of approach work on each side. And then again, finishing touches, seed and sod, the regrading the slopes, some repair work on the existing wing walls, seeding and sodding. The county wanted to come in and apply a thin epoxy overlay on both of these bridges. And they were able to do that on 408, which was the bridge that was done first. So on 408, they came out before opening to traffic and applied a thin epoxy overlay for a protective wearing surface on top of those precast deck panels, and epoxy and grouted joints and the deck joints between the elements. Unfortunately, on 409, due to weather limitations, they were not able to put the epoxy overlay on. We were out there just this year and found that, or beginning of this year, and found that it has the deck without an epoxy overlay has performed great. They still plan on doing it sometime this year, but so far the deck joints and grout pockets are performing very well, and we don't see any cracking. Finally, guardrail was installed, and the slopes were restored with grass seed. So, in conclusion, the goals of these projects were met. Both these projects were met. We used a cost-effective system, the lowest cost system, and got a 60-year plus service life on these bridges. What was the completed cost? $180,000 for Bridge 408, which included all of the material, labor, overhead, and equipment that the county brought out to do the job, and where we were able to finish that project. The county was able to finish that project in 10 working days. The next bridge, 409, was the 35-foot span bridge, and that was completed for a cost of $222,000. Again, including all of the material, overhead, and equipment. And that was also done in a total of 10 working days, and was reopened to traffic after 10 days. So 2 bridges done basically in a period of a month, with 2 road closures for full closures for 10 days each. The county was very happy with that, and that limited amount of closure on this very busy roadway. And then in conclusion, the superstructure was 80% less expensive than it would have been for the DOT to come in and completely replace these. That's based on a reconstruct fee of a little bit over $1 million, and we spent near $200,000. So spent a 20% of the funds to get a reconstructed bridge with plus 60-year service life. And really, we did it in 90% less, with 90% less traffic days. Again, that assumes about a 4-month typical closure to do a full reconstruct of a bridge. Typically, a Michigan winter is we have about 4 months to get in and get out before winter. And wanted to thank Bill Hazelton, the Director of Engineering at St. Clair County, and Dwayne Rogers, at the project manager at St. Clair County, for helping me put this together. They actually presented with me at the Michigan County Engineers Conference, and kind of fed in their pieces as needed. But with that, I think I went a little fast here. I can back up and talk about specific elements of the press brake form steel tub girder if anybody wants to hear more about that, or anything about the galvanizing process if need be. So we're pretty early here, and wanted to kind of open it up to any questions if anybody had questions. I'm looking back to see if there was anything. Looked like maybe there was just some items about getting audio, but no specific questions. I'll wait a few more minutes and see if anybody has any questions. We have a question here from Thomas Schuler. Common thickness of steel, depth of girder. Yeah, that's a great question. Our standards, if we go back to the cross section, we follow, as far as depth of the girder, we follow AASHTO, AASHTO LRFD recommendations of the span length over 30 for the depth of the tub girder itself, and overall depth of the span over 25. I think as the structural engineers will know, we can design for pretty much any depth, but usually what winds up controlling is the live load deflection requirements. So the stiffness basically is what typically controls the design. It's not controlled by strength. Our thickness of the steel, we keep everything to 3/8 of an inch. Again, that goes back to the fact that strength is not a design constraint. It typically is the constraint is typically the live load deflection. So 3/8 thickness is minimum thickness typically used for flange elements, and we keep the whole tub girder at 3/8 of an inch thick. And again, depth of the tub girder we keep to span length over 25. Good question. Another question we have: are there any plans to get approvals in additional states like Wisconsin? Yes, we are marching forward. We are submitting. It's a slow process. Every state has their own requirements, and we follow. For each state, we submit a pre-qualification package, which is about a 300 to 400 page document that outlines designs and the elements that are specifically designed for each state. So Wisconsin is definitely on our radar for getting Con-Struct approved and getting these press brake form tub girders. We have just to let you know, we have submitted to Arizona, to Illinois, to additionally to North Carolina. So we are picking away at it as we have time to develop our pre-qualification package. Every state has their own system for submitting new products, and we kind of try to follow those systems. And then it is a very long review process, kind of a back and forth. We also submitted to Pennsylvania, and we are in that back and forth process right now with Pennsylvania. So yes, good question, and yes, we will look at getting approvals in Wisconsin also. Another question: are there any fatigue problems that you have noticed in this type of existing bridges as of now? No, no fatigue problems. That is something that SSSBA is planning on doing more research with their alliance partners, with their steel manufacturers, as far as fatigue on a bend. But as far as we know now, there are no fatigue problems associated with these. Are relatively new. There really hasn't been a system that we can go to that was put in the 70s that we can look at. The earliest bridge we have out there is a bridge built in 2004 in Michigan, and as far as that bridge, there's no deterioration at all. I mean, we don't see any corrosion, any loss of coating. So there's really they haven't been out there long enough. But again, we don't foresee any problems in fatigue because we're bending it in accordance with AASHTO and AISC, which really doesn't damage or cause any cracking of the plate itself. So I hope that answers the question. But no, there's nothing out there except for there's a lot of cold form steel out there, and there is research on cold form steel through AISC, but nothing specifically with the press brake form steel tub girder. Hope that answers that question as best I can. Another questions. Limitations to go beyond 80-foot span lengths. Again, another great question. Obviously, plate only comes in standard widths. We can get up to 120-inch widths right now, but once you get over the 8-foot width, which is 96 inches, the plate gets more and more expensive. So we start losing our economy when we get span lengths over 80 feet because we have to start using plate that is wider than our manufacturers have in stock, and we have to special order the plate. So 80 feet was a span length. Two things. We also have manufacturers that need to be able to pick up and freight the bridges. So 80 feet puts our bridge unit at about, I think it was about 30 tons. For an 80 foot, our standard widths are 7 feet wide. So at 80 feet, 7 widths, we're about at a little bit over a 30-ton unit, and kind of that's where we felt was about the limit as far as the economics of it. It just gets more and more expensive as we get. Not that it can't be done, but we just need to develop. Again, just like the galvanizing has developed to 80-foot spans, and the press brake goes to 60 feet. We just need to develop longer press brakes, have standard width plates, wider, and galvanize, be able to galvanize longer spans. Again, 80 feet is about as long as we've found that we can progressively dip the largest tub girder section we currently have. So another good question. Thank you. I'll wait a few more minutes and see if we have any further questions. We have another question. PDH certificate available for bridge erector. I would say you for that question you'd have to go to AGA, who hosted this, and see if they have PDH certificates for the presentation. And just making sure I didn't miss any questions. So with that, I like to thank you for being at my presentation, and I hope this helped. And if you do ever have any questions, by all means, contact me anytime. Again, I'll go down to my contact information. It's here. I work for TEG Engineering, and you can contact me anytime at gnelson@tegcivil.com. And you can also look at our website for the Con-Struct Bridge, which is www.constructbridge.com, and find any more research and specific project pictures that you can think of. You can also post questions to that website, and they come directly to me. All right. So with that, wanted to thank you and conclude this webinar. Thank you very much.